Hi class. So welcome back to our recording for lesson 8 for EE2165. And for this lesson we will talk about second order circuits. But in principle, lesson 8 or second order circuits is just a continuation of lesson 7, which talks about first order circuits, and both lessons 7 and 8 talks about transient circuits. But in the previous lesson, we have learned about simple RL and RC combination circuits. But for this lesson, we will tackle a combination of the three circuit elements: resistors, capacitors, and inductors into a single circuits, or RLC circuits. So this is a little bit more complex compared to the previous lesson, and for that we will go into the analysis of RLC circuits using second order differential equations, but we will not go through the differentiation process, but instead let us go directly into the formula for the sake of time and of course simplicity. So what makes this lesson unique is that number one, we will have two energy storage elements in our circuits. Instead of having one, either only capacitors and inductors, we will have both of them as energy storage components in our circuit. So this means that the energy can flow from both storage elements and can also be dissipated in the resistor. So that makes the analysis a little bit more complex. And the second one is that the concept of time constant will not be used or is not applicable for second order circuits any longer. Instead, we will tackle the term damping, which describes the gradual loss of energy in our RLC circuits. So those are the two main differences from previous lesson, but the goal of this lesson is practically the same as that of the previous lesson. So this lesson has 4 topics. We have source-free RLC in series. Second is source-free RLC in parallel. Third and fourth are series RLC and parallel RNC with a source. So starting off with source-free series RLC circuit, we have this circuit diagram here. So all of the three elements, resistor, inductor, and capacitor, are connected in series. So for source-free series RLC circuit, we are interested to find the current, because in a series circuit, the current is the element that is the same or equal for all of the elements connected within that same loop. So to include all of the elements, it is advantageous for us to use the current, and if we want to find the voltage, then we can just use Ohm's law further. So the second order differential equation that describe the circuit is given by this equation here, as you can see on the screen. So the second order differential equation is denoted by d squared I over dt squared. So we have all elements R, L, and C in that equation, but skipping all the process of differentiations, we can obtain instead the characteristic equation, which has the variable s in it, where I is equal to a e to the power of st, and this entire term for the current are constants to be determined later on. So right now, let's focus on the quadratic equation s squared plus r over ls plus 1 over lc is equal to 0. So it is worth noting that this equation is in quadratic form. So meaning we have two possible roots as solutions for this equation. So the easiest way to do that is to use the discriminant of the quadratic equation. So This following formula describes a more compact way of solving the roots from the coefficients or constants of these characteristic equations for our series RLC circuit. So we have roots S1 and S2, which are expressed in both alpha and omega. We have S1 and S2 plus and minus. So the corresponding values for alpha and omega are also given in equation 2, which are in which R, L, and C are all constants or coefficients given from our sample circuit. So first is we can solve alpha and omega, then second is then we can proceed to solve the roots S1 and S2 by just simple substitution. So, just a little bit of a reference, the roots S1 and S2 are called natural frequencies, while alpha and omega are called resonant frequencies. So, these are both frequencies. We would like to describe them as frequencies because of the damping characteristics of our LC circuit. So damping is a term that I've just previously mentioned. Instead of time constant, we will use the term damping. And damping is the gradual loss of the initial stored energy of the RLC circuit due to the presence of the resistance R. So this is the same behavior concerning the resistance R even from the previous lesson. So the role of the resistance R is to act as load, and therefore it consumes or dissipates the energy stored by our storage components or elements, capacitor and inductor. So we can recall from the previous lesson that a source-free circuit will eventually lose its initially stored energy. So the time it takes for this energy to be dissipated is described by the time constant from the previous lesson. In the case of our RLC circuit, we will use the term damping to describe the gradual loss of initially stored energy. So, no more usage of time constant, but instead we will use the term damping. We will not use the term time constant for second order circuits because time constant is just limited for application of RL or RC circuits. The quantities alpha and omega are very important in describing the damping behavior of the circuit. So we will tackle that later on. So right now, let's go back to the roots S1 and S2. Having these roots meant that there are two solutions for the current equation I indicated above. So this equation I, or the one that you can see on the screen at the moment. Therefore, the total natural response of the series RLC circuit is given by A1E S1T plus A2E S2T. So we have S1 and S2, and we also have A1 and A2, which are constants to be determined from initial values of the circuit. So the same with the concept from the previous lesson, we have initial and final values, but on this lesson we will use the constants A1 and A2. So for source-free series RLC circuits, we have these two equations which will help us to determine the initial values or initial parameters of our circuit. So we have I sub O is the current at the start, while DI sub O over dt, or the first derivative of our current equation expressed in terms of time, is given by negative 1 over L parenthesis R I sub O plus V sub O. So L, R are given from our circuit equation, while I sub O plus V sub O are initial conditions or initial values that we have to determine from the circuit still. So the prerequisite to finding the roots S1 and S2 are alpha and omega as expressed in these equations. So we need to solve for equations 2 first before we can proceed to solving the equation 1 or the roots of the quadratic equation. As previously mentioned, these quantities will help us determine the damping behavior of the circuit. By looking at the values of alpha and omega, we can determine the next step for solving for I sub t, for I in terms of t through the nature of the roots and without going through the entire process of going through the quadratic characteristic equation. So now that we have two possible roots S1 and S2, the next thing that we can determine is the three path or types of solution that we can arrive on as we solve this quadratic equation. So instead of going through the hassle of solving the entire equation itself, we can determine from first step, from that step where we are solving for alpha and omega, uh, the damping case for our source-free series RLC circuit. So we have three conditions for that, and we can only have one of these three conditions at any particular instance of our circuit. So if we have particular values for RL and C, and of course the configuration of the circuit, we can only arrive at only one of these three cases. So first case is when alpha is greater than omega. So in this particular case, we will have an overdamped case. Now second case is when alpha is equal to omega, then we have a critically damped case. And the cases 1 and 2 are quite similar, and it is almost difficult rather to tell the difference for the two. But for the third case, in which alpha is less than omega, then we have an underdamped case. So again, just to remind you that the definition of damping is the gradual loss of the initial stored energy of the RLC circuit due to the presence of the resistance R. So we have overdamped, critically damped, and underdamped cases. And these three conditions or cases apply all throughout our analysis of RLC circuits. So for our four topics, we have series, parallel, RLC, source-free, and with source. These three cases will still apply. Now, for our first case, which is the overdamped case, so for source-free series RLC circuit, this is the graph that describes the overdamped case. And again, this is described as alpha being greater than omega. So if this is so, then it means that the roots S1 and S2 are negative and real. Therefore, our total natural response is given on equation 3.1. So we have A1 and A2, which are constants to be determined from initial conditions, and of course our roots S1 and S2. And again, in a source-free circuit, our current IT decreases as T increases or as time goes by. Next, we have the type 2, which is the critically damped case, and this is characterized as alpha being equal with omega. So if alpha is equal to omega, then our roots S1 and S2 are equal. Therefore, our total natural response is given by equation 3.2. So instead of using S1 and S2 as the exponent for our Euler's constant, we will use alpha instead. And our third case, which is the underdamped case, the graph is slightly a bit more different compared to the first two cases. And the underdamped case is described as alpha being less than omega. So if this is the case, then the roots S1 and S2 are imaginary. So we will tackle imaginary numbers, and our total natural response is given by equation 3.3, in which B1 is equal to alpha plus a1 plus a2, b2 is equal to a1 minus a2, which is an imaginary number indicated by letter j, or in other cases, especially in your scientific calculators, j can be indicated as I, or simply that the expression is imaginary, is an imaginary number, and of course omega d given by this third line in the equation. The presence of sine and cosine functions are due to the presence of imaginary roots and by the application of Euler's identities. So sine and cosine functions are an indication that our underdamped case exhibits an oscillatory response. And also the presence of sine and cosine functions are because we are using the using Euler's identities to substitute for these imaginary identities. We have an oscillatory response because of the back and forth flow of energy between the two storage elements, capacitor and inductor. But with the presence of the resistor, the oscillation gradually decreases, as some of the energy will also be dissipated through the resistor. If the circuit resistance is 0, we would expect a perfect oscillation and the amplitude to be constant. This somehow gives us a glimpse of what an alternating current or AC electricity looks like. So if this graph is to be is to have if this particular case is to have no resistance, then this oscillation should be perfect and should retain its amplitude at infinite time towards infinity. So before proceeding, maybe we will have to solve a sample problem which involves a source-free series RLC. So at this juncture, let us solve a sample problem which involves a source-free series RLC circuit. So look at the diagram on the screen. So the switch is closed before t is equal to 0, or there are two parts in terms of time for the solution, and the part 1 is when we have to solve for the initial conditions when the switch is still closed, and part 2 is when at t is equal to 0 the switch is open, and that's when our series RLC circuit becomes source free. So just to clarify that the voltage source is there to give the capacitor and inductor an initial charge or initial energy to be stored, and then once the switch is open, the voltage source will not have a bearing for the series RLC circuit anymore. So again, we have two parts to solve the solution. We have part 1 is when the switch is closed, before t is equal to 0, and when the switch is closed, we have learned from previous lesson that the capacitor becomes open circuit and the inductor becomes a short circuit. So for the branch that involves the capacitor, even the 3 ohm resistor will not have a bearing anymore. So let's just redraw that circuit. You have 10 volts, then we have 4 ohms, then we have an open circuit here just to indicate that the capacitor becomes open circuit, and then we have a 9 ohm resistor, and of course our inductor becomes short circuited. So to solve for the initial current I, when t is equal to 0, I is by Ohm's law equal to 10 of V over R, and our V is equal to 10 volts, then our R is equal to 4 plus 9, then we have 0.769 amperes. Then our voltage when t is equal to 0 excuse me, we have 9 times current of 0.769, our voltage then is equal to 6.92 volts. So our current is the initial current through the inductor, and our voltage is the initial voltage across the capacitor. So these are like the initial charges for both capacitor and inductor. So part 2 is when the switch is opened. At t is equal to 0. So our circuit slightly changes. And then we have the capacitor back on the line. We have the resistor and then the inductor over here. And then another resistor. Connected all together 0.02 farads. We have 3, we have 9, and then we have 0.5. So that's the circuit, the equivalent circuit. Then what we can do next is we can solve for alpha and omega. So our alpha from this equation is equal to R over 2L equal to 9 plus 3 over 2 times our L is 0.5 henries, and our alpha is equal to 12. Then our omega is equal to 1 over square root of LC, and our omega is equal to 10. So we have alpha and omega being equal to 10 and 12 and 10 respectively. So since alpha in this instance is greater than omega, the response is overdamped. Just to mark it like that. So if our response is overdamped, as in the first case, we can approach the solution by trying to obtain this equation 3.1. But before we can do that, let us solve for the roots S1 and S2 first. So we have the formula for the roots. Over here, and then we can add negative alpha plus or minus square root of alpha squared minus omega squared. So for S1 we have negative 12 plus square root of 12 squared minus 10 squared. Our S1 is negative 5.367, and our S2 is equal to negative 12 minus square root of 12 squared minus 10 squared. Our S2 is equal to negative 18.633. So these are dimensionless quantities. We don't need to add a unit of measure for these. Then we can solve for the current equation. Current equation for overdamped case. So just a recall, our current equation for overdamped case is given by equation 3.1. So we have I in terms of t is equal to a sub 1 e s1 t plus a2 e s2 t, which is equal to a1 e negative 5.367 t, pardon for my handwriting, very ugly, plus a2 e s2 is negative 18.633 t. But it doesn't stop here. Just to write it down. We still need to solve for constants a sub 1 and a sub 2. And this is where the process becomes a little bit lengthy. It's not that complex, but it just requires a little amount of time. So just to recall that our constants a1 and a2 will depend on this equation, excuse me, on this equation right there. So we have I when t is equal to 0 is given by 0.769 amperes, and then the first derivative of our equation I in terms of t, di or dt when t is equal to 0 is given by negative 1 over L R times I in sub O plus V sub O equal to negative 1 over 0.5 12 times 0.769 plus 6.92, and that is equal to 32.3 ampere per second. So we have a value for both initial conditions. And then we can solve for our equations only for a1 and a2. So this is a little bit lengthy, and I hope that you will have the patience to bear with it. So at t is equal to 0, I is equal to 0.769. So we will just substitute that in our equation here. So we have 0.769 is equal to a sub 1 e 0. So when you multiply the entire expression with 0, then it becomes 0, no brainer, plus a2 e0. So basically what's gonna happen here is that the Euler's constant or the Euler's constant will not have a bearing anymore, and so 0.769 is equal to a1 plus a2. So that's our first equation. Now let's solve for the first derivative of this equation again. So we have di over dt. So the derivative of an expression that involves an Euler's constant is that you will just bring down the exponent. So that becomes negative 5.367A1E, negative 5.367T, minus 18.633A2E, negative 5.367T. So when T is equal to 0, the same thing will happen to the Euler's constant. It will not have a bearing anymore. So di over dt is equal to negative 5.367 a sub 1 minus 18.633 a sub 2. But then our di over dt is already found here. So let's equate this with 32.3, and then that becomes our equation 2. So simultaneously solving for 1 and 2 yields, and I'm gonna skip most of this process. So A1 is gonna be 3.51, and A2 is equal to negative 2.74. So you can solve your own problem if you want to go through the tedious process of it. Now, our final step of the process, our current equation is, as you can see here, we've already solved for A1 and A2, and we can just simply substitute it directly to here. You have I is equal to 3.51, wait, 3.51 e negative to the power of negative 5.367 t minus 2.74 e to the power of negative 18.633 t amperes. So that is the equation for a current, and this is our final answer. So the remaining variable for this equation is the time t. So if you are given a particular time, then you can just simply directly substitute that in here, and you can obtain a constant value of current I. So that's it for our source-free series RLC circuit. I hope that you will bear with my messy solution. Now for the second topic for this lesson, we have source-free parallel RLC circuit. So our approach for parallel RLC circuit, which is source-free, is a little bit different, but mostly the same with that of the series circuit. So for source-free parallel RLC circuit, we are interested to find the voltage because in parallel circuits, the voltage is the same for all elements connected. We have learned that from the previous lessons. Now, for the circuit that you can see in your screens, the second order differential equation that describes this is given by this equation right here. So, getting a shortcut from the differentiations, we can obtain the characteristic equation, which is a quadratic equation expressed in terms of S. So this is highly the same as with that of the previous lesson, previous topic. So we have the roots S1 and S2, which is still the same with that of the series circuit, and in fact the same with the circuits with a source. So in order to solve the roots S1 and S2, we have alpha and omega Omega is the same, but alpha is a little bit different. So in the previous lesson, we have two r over 2l, but in here we have 1 over 2 rc, and then omega is still the same. So based on the values of alpha and omega, the damping conditions still apply, and its corresponding waveforms is presented here. So for the three conditions, we have overdamped case, critically damped, and underdamped case. Um, these conditions will still apply. So for type 1 overdamped case, we have this equation given in equation 4.1. For type 2, which is critically damped case, we have equation 4.2, and for underdamped case, we have equation 4.3. So this is just a matter of substituting the values class. There is nothing very complicated going on here, but for the values of a1 and a2, which you can find throughout these equations, these constants can be determined from initial values of the circuit as indicated in these equations. So we have v sub 0 and then dv o over dt. So these equations are given for source-free parallel RLC circuits and should not be used elsewhere. So this will give us a leverage or a formula in going through the solutions. I hope that you will take notice of these differences, but because they look exactly the same at first glance. So right now, let's solve a sample problem involving source-free parallel RLC circuit. So if our resistor has a value of 1.923 ohms, our inductor at 1 Henry, and our excuse me, our capacitor at 10 millifarads, and assuming that our voltage at the start, or our voltage when t is equal to 0 is equal to 5 volts, and I at the start is equal to 0 amperes, let's find Vt. So most of the what you call this constants of the problems are already given, so that makes our approach a little bit easier. So we will start directly with finding alpha and omega. So again, our alpha is equal to 1 over 1 over 2 RC for source free parallel. So substituting those values, 1.923, and then our C, oh my god, I just have to be ugly, to 1.923, then we have 10 times 10 to the negative 3 farads, indicating the millifarad, and then we have alpha to be equal to 26. Our omega is equal to 1 over square root of LC is equal to L is equal to 1 Henry, capacitance is equal to 10 times 10 to the negative 3 farads, and our omega is equal to 10. So since alpha is equal is greater than omega, the response is overdamped. So solving for roots, S1 and 2 is equal to negative alpha plus minus square root of alpha squared minus omega squared. So we have S1 is equal to negative 26 plus square root of 26 squared minus what do you call this, 10 squared, our S1 is equal to negative 2. S2 is negative to negative 26 minus the radicand. Okay, S2 is equal to negative 50. So the voltage equation for overdamped case overdamped, okay, we will use equation 4.1. Yeah, Vt is equal to A1E, our S1 is negative 2, then T, plus A2E, our S2 is negative 50 T. But it doesn't end here yet. We still have to solve for A1 and A2. And this time, solving A1 and A2 will involve the values from the initial conditions. So if at T is equal to 0, our voltage is equal to 5. So that's indicated by V when T is equal to 0. So let's substitute that on our equation. We have 5 is equal to A1, and again, if you will have the Euler's constant E to the power of 0, then that is basically equal to 1. So let's just skip that, and the same is true for A sub 2. So this is our equation 1. So getting the first derivative, of our equation Vt, so we will obtain dv dt. So again, from this equation over here, we can just easily derive that by bringing down the exponent of the constant E. So we have negative 2 A sub 1 E negative 2 T minus 50 A sub 2 E negative 50 T. But also, dV when T is equal to 0 is given by this equation. So we have negative VO plus R I sub O over RC. So that's 5 plus R times I sub 0, in which our I sub 0 is equal to 0 amperes. So multiply that and we will have 0 still. And we have R to be equal to 1.923 times C, which is equal to 10 times 10 to the negative 3 farads. And so we have negative 260. So if T is equal to 0, our dV dt is equal to negative 260. So let's substitute that over here. So our dV dt is equal to negative 2.60 equal to negative 2 A1 minus 50 A2. So this becomes our second equation. No. simultaneously solving 1 and 2 yields a1 to be equal to negative 0.2083, and then a2 is equal to 5.208. So just to skip the entire process of elimination, substitution, and things like that. Therefore, our voltage equation is Vt is equal to negative 2.0, no, negative 0.2083 e negative 2t minus, no, plus 5.208 e negative 50t volts. And that is our final answer. So there you have it. This is our source-free parallel RLC circuit. So for our third topic for this lesson, we have series RLC circuit, this time with source. But in essence, class, this topic builds so much from the series RLC circuit without source. So we will borrow a lot of formulas from the first topic. If you're gonna look at the diagram and apply KVL, we will obtain terms in terms of expressions in terms of voltage. So this is the resulting second order differential equation. But for the rest of the quantities, for example, for roots S1 and S2, this is still the same from the first topic. Alpha and omega are still the same from the first topic. But what makes this unique is that the complete response this time is composed of two parts. We have transient response and the steady state response. We have learned this from the previous lesson that if a circuit has a source, then we can solve our solution rather has two parts, and this is it. So for the transient response, we have the same cases and the same conditions for damping. So for each damping case, we have a corresponding transient response in terms of voltage. I know this formula are already so familiar to you at this point, so I'm not gonna explain that further. But for the steady state voltage, this is the final value of V. So this is also the same across all cases in which our steady state voltage, or Vs, is equal only to our source voltage right here. So whatever our source voltage it is, then that's our VSS. Therefore, the complete responses for each case is simply the transient response plus VSS, which is equal to source voltage, and this is indicated for each damping case right in your screens. This time, let's proceed to the parallel RLC circuit with source, because they are highly equal and the formula that they are using are more or less the same except for the value of alpha, which of course has to take into account whether the circuit is series or parallel. Now, applying KCL for the parallel RLC circuit gives the second order differential equation expressed here, which is in terms of current. The roots S1 and S2 as well as omega are still the same, nothing much to explain further, as well as the complete response, which is equal to transient response plus steady state response. But then the complete responses for each cases are expressed in terms of currents, and our steady state current is indicated by IS. So those are the series and parallel RLC circuit with source. Now, what do you call this? Solving for sample problem which involves series RLC circuit with source. So in this problem we are asked to find VT. Now, our part 1 for this solution is that when the switch is closed before t is equal to 0, so when our switch is closed, our capacitor becomes open circuit and our inductor becomes short circuit. So our equation, no, our diagram is simply composed of the 24 volt source plus our R, in which in this case is equal to 5 ohms. So we have 5 over here, and then our 1 ohm resistor right over there. So our current at t is equal to 0 is given by 24 plus 5 plus 1 is equal to 4 amperes, and our VO is simply equal to 4 amperes times the resistance value at 1, so that is also equal to 4 volts. So IO is simply the initial current through our inductor, and our VO is simply the initial voltage across the capacitor. So these are our initial values. Now part 2 is when the switch is opened. At t is equal to 0. So our inductor and our capacitor are back on the line, but our 1 ohm resistor will be discarded. So redrawing the circuit once again, we have 24 volts. We have the 5 ohm resistor above, 1 Henry inductor, and then our capacitor valued at 0.25 farads. Now, the next process is to solve for alpha and omega. Our alpha is given by R over 2L. We have 5. 2 times 1 is equal to 2.5, and our omega is given by 1 over square root of LC, then 1 over square root of 0.25 times 1, and that is equal to 2. Since alpha is greater than omega, our response is overdamped. The next thing that we will do is solve for roots S1 and S2. So we have S12 is equal to negative alpha plus minus square root of alpha squared minus omega squared. So we have S1 is equal to negative 2.5 plus square root of 2.5 square minus 2 squared. Our S1 is valued at negative 1. Our S2 is negative 2.5 minus square root of 2.5 squared minus 2 squared. Our S2 is equal to negative 4. So our voltage equation for overdamped case is given by this one, overdamped. Vt is equal to Vs plus A1 ES1t plus A2 ES2t, where Vs is equal to our source, 24 volts. So Vt is equal to 24 plus A1 E negative 1t plus A2 E negative 4t. So that's the voltage equation. Now what's missing here is we just have to solve for A1 and A2, our constants. Wait. So at t is equal to 0, our voltage when t is equal to 0 is equal to 4. So let's substitute that directly. We have 4 is equal to 24 plus A1. We don't have to write E because it's still equal to 1 plus A2. So we have A1 plus A2 is equal to negative 20. And that's our equation 1. Now, taking the first derivative of Vt, we have dv dt is just a matter of bringing down the exponents. We have negative a sub 1 e negative t minus minus 4 a sub 2 e negative 4t. But we have this expression I is equal to c dv over dt. Therefore, our dv dt in this equation is equal to I over c, and our I from initial conditions I0 is equal to 4 amperes, and our capacitance is equal to 0.25. So we have our dv dt to be equal to 16 volts per second. So substituting the value of dv over dt in the first derivative, we have 16 is equal to negative a1 minus 4. No, before we substitute that, we just have to at t is equal to 0, dv dt is equal to 16. So we have 16 is equal to negative a1. We don't need to write the rest because the exponent is 0, and therefore that's equal to 1 minus 4a2. So that's your second equation. Simultaneously solving if you will simultaneously solving n1 equation 1 and equation 2 yields that the value of a1 is equal to negative 64 over 3 while a2 is equal to 4 over 3. Therefore, our voltage equation is Vt is equal to 24 plus our a1 negative minus a1 64 over 3 e negative t plus 4/3 e negative 4t, or by just further simplification, Vt is equal to 24 plus 4/3 negative 16 e to the power of negative t plus e to the power of negative 4t volts. And that's our final answer. If you will substitute it with a particular value of t, then you can obtain a constant value of V. But yeah, this is our final answer for the series RLC circuit with source. The entire solution is highly methodical, so I suggest that you take caution in solving the problem, making sure that you are solving it step by step, not missing on anything. Be careful on your solution, and to somehow compare this with other problems, because that way we can get familiarized with the entire process. So that's it for this lesson. Thank you so much and stay safe.